Geology students, this is the second video for this week. It's going to be called Spring29. Previous video we talked about fossils because we're going to get into that in the fossils lab, but we're going to start chapter 8 today. And this is straight out of your book, Precambrian Earth and Life History, the Hadean and the Archean Eon. Got to get that geologic time scale in your minds, ladies and gentlemen. You got to memorize it. So let's go over all these words in the title. You should know what all these words in the title mean. Precambrian, Hadean, and Archean. Remember, there are 4 eons of geologic time. The Hadean Eon, which is from 4.6 billion years ago to 4 billion years ago. Then we got the what era? The Proterozoic Eon. And it goes from 4 billion years ago till 2.5 billion years ago. $4 billion years ago to 2.5 billion years ago. And then later on we'll talk about the Phanerozoic. I'm sorry. Good Lord, I'm an idiot. It goes from the Hadean from 4.6 to 4 billion years ago. Then it goes to the Archean Eon from 4 billion years ago to 2.5 billion years ago. And then we go to the Proterozoic Eon. And it goes from 2.5 billion years ago to 542 million years ago. 2.5 billion to, I hate it how it just changes what you want to write in here. Anyway. Okay, and then we go to the last one, the Phanerozoic Eon, which goes from 542 million years ago to now, or to today. Okay, there you go. Screenshot it right there. You need to know that. So on the next test, there might be a question. A rock is, let's say it's 3 billion years old. What eon did it form in? Looking at this chart, what eon would it have formed? If it formed 3 billion years ago, would it have been A, the Archean, B, the Hadean, C, the Phanerozoic, or D, the Proterozoic? If it's 3 billion years ago, it must have formed during the Archean Eon, right? Okay, now this is historical geology. So we're going to begin our study of Earth history with the first eon of geologic time called the Hadean. The other thing you need to know is, what does this word mean, Precambrian? Precambrian means anything before the Phanerozoic Eon. In other words, anything from 4.6 billion years ago up to 542 million years ago. Why do we call it the Precambrian? Because the first period of the Phanerozoic Eon is called the Cambrian. So anything that occurred before the Cambrian occurred before 542 million years ago. So before you even get the chapter started, you got to know what these terms mean. Okay? Let's take a look at geologic time. Again, this is memorization. You got to be able to memorize this. The first eon, if you looked at Earth history as a 24-hour clock, you can see that the Precambrian represents more than 21 hours of a 24-hour clock. So that this last bit in orange, called the Phanerozoic Eon, is only the last 3 hours and 50 minutes out of a 24-hour day. If you wanted to compare it to a 24-hour clock, the blue areas are Precambrian. First eon, don't forget it's the Hadean, then the Archean, then the Proterozoic. We divide the Phanerozoic Eon, which we'll be talking about for the final exam, into 3 eras, or eras, depending on what part of the country you're from. Paleozoic, Mesozoic, and Cenozoic. But now we're going to begin Earth history by talking about the Hadean Eon that goes from 4.6 to 4 billion years ago. This is what an artist's depiction of what the Earth looked like when it was born 4.6 billion years ago. This is the very beginning of Earth history. And I kind of like looking at this oil painting, or it might be a watercolor. It looks like an oil painting. What can you glean from this? Well, when you think of the Hadean, it looks like Hades, fire and brimstone. You have the Earth covered by molten lava. The Earth was much hotter back then. The first rocks started to form. And look at the moon. Look how close the moon is to the Earth. The moon, don't forget, came from the Earth. A long time ago, the moon, an object struck the Earth and a molten blob was sent into orbit, which cooled and coalesced to form the moon. The moon is moving away from us. So in the past, the moon must have been much closer to the Earth. So the gravitational pull of the moon must have been much higher. So we had high tides and low tides of lava running onto these little chunks of rock that would eventually become the ocean floor, the sea floor. But back then, there was no water yet. Why? Because what do you think happened when it rained back then? It was so hot that it just evaporated and went back into the atmosphere to form clouds. But after millions or tens of millions of years of raining, do you think the Earth might cool down? Yes. So slowly the Earth started to cool down. So you had solid rock on the surface. But back then, 4.6 billion years ago, at the beginning of the Hadean, this is what we think the Earth looked like. And looking at this picture, I think you could come to the logical conclusion that life could not exist on the planet back then, 4.6 billion years ago. Why? Because this lava was anywhere from 12 to 1400 degrees Celsius, or something like 1700 to 2200 degrees Fahrenheit. It would have burned any organic matter. We don't think life could have existed 4.6 billion years ago at the beginning of the Hadean Eon. The oldest Earth material found from our planet are these zircon crystals. Zircon is a type of mineral. Now, these zircon crystals have been dated as being 4.4 billion years old. We don't have any 4.6 billion year old rocks on the planet, but we know the Earth must be at least 4.4 billion years old because of these zircon crystals, which are found in Archean rocks. Rocks between 4 and 2.5 billion years old have these little crystals, ancient crystals from even older rocks that no longer exist. So these are inclusions in Archean rocks. How do we know the Earth is 4.6 billion years old when the oldest materials are 4.4 billion years old? We know that because when the astronauts came back from the moon, they found rocks that are about 4.6 billion years old. We found 4.6 billion year old rocks on Mars. We find them on meteorites. And we know the whole solar system formed at the same time because of the solar nebular theory. And so therefore the Earth must be 4.6 billion years old. What happened to those old ancient Hadean rocks? They got destroyed through the rock cycle. They might have been melted and formed new rocks. They could have been metamorphosed and changed. They could have been eroded away. This is the last evidence we have from back then. Think about it like this. The further back in time you go, the harder it is to find evidence because rocks get destroyed through the rock cycle. First thing that happened that was important is, going back to this picture, you can see that you have little chunks of rock that started to form and cool as the Earth cooled down. Eventually you would form little islands, and these islands would collide together to make bigger islands, and bigger islands. So we had the beginning of the formation of continental crust and oceanic crust. So we started to form solid rock on the surface, continental and oceanic crust. And this all, by the way, all of this started to occur during the second eon of geologic time, called the Archean. So by Archean time, we now had water, we had oceans, we had islands making bigger, smaller pieces of continental crust. We had oceanic crust in this dark blue. How do we know that this actually occurred 4 to 2.5 billion years ago? Well, we're going to have to look at the evidence for that, aren't we? So we'll do that. Now we're in the Archean Eon, which goes from 4 billion years ago to 2.5 billion years ago. We pretty much skipped over the Hadean pretty quickly, right? Because there's no rocks left from that. There's only little chunks of zircon from the Hadean that are in Archean rocks. There are no rocks from the Hadean. So before we go onwards and forwards, let's take a look at where on planet Earth can we find Precambrian rocks. In other words, where can we find rocks that are older than 542 million years old? So you need to take a good close look at this map of the world. There's Tennessee right here, Greenland, South America, Africa, Kamchatka in Russia, India, Japan, Australia. Okay, but you want to pay attention to 3 main colors. Red, those are called shields. Green, those are called platforms. Green's called platforms. And the light brown areas are called orogenic belts. Orogenic belts, meaning mountain belts. Okay. So, the red areas, which we call shields, are places where we can find Precambrian rocks that are older than 542 million years old, on the surface of the Earth. So in Tennessee, which we're right over here, we don't have barely any rocks that are older than 542 million years old. We don't have any at all. In fact, you have to go to North Carolina to see it. For the North American continent, most of the shield is up here in Canada. Ontario to Quebec to Northwest Territories, you can find rocks that are older than 542 million years old, Precambrian rocks exposed on the surface of the Earth. You can see every continent has some shield, some places where you can find Precambrian rocks on the surface of the Earth. The green areas are called platforms, and in all of these green areas you can find Precambrian rocks, but they are underground and covered up by younger rocks. They're covered by Phanerozoic rocks. But if you drilled down deep enough, you'd still get the Precambrian rocks. So platforms are places where you have Precambrian rocks that are covered up by Phanerozoic rocks, covered up by younger rocks, but there's still rocks there. In the brown areas called the orogenic belts, there are no Precambrian rocks. Think about what that means, ladies and gentlemen. In the light brown areas, in the orogenic belts, there are no Precambrian rocks. Bottom line is, these areas in light brown did not exist 542 million years ago. So the continents have grown bigger over the last 542 million years. This part of Australia, Eastern Australia, didn't even exist 542 million years ago. New Zealand didn't exist. The islands of Japan did not exist. Iceland did not exist. Now the last word we need to get comfortable with is a craton. What is a craton? C-R-A-T-O-N. T-O-N. is equal to a shield plus a platform. A craton is a shield plus the platform. So let's take a look and see what that means. Here's the shields in red. If you take into account the areas in red and green, those are the cratons. On the craton, you can find Precambrian rocks, rocks that are older than 542 million years old, either on the surface of the Earth as in a shield or underground as in a platform. So if you take the red and green together, we call those cratons. And the cratons are the ancient hearts of the continents. They're the most ancient part of the continents are in the red and green, whereas the orogenic belts, the light brown areas, were formed much later, after 542 million years ago, in other words, during the Phanerozoic Eon, and they were added on. All of Indonesia was here. These islands were added after 542 million years ago. Next thing we're going to take a look at, we're going to make a list of what kinds of rocks we find in the Archean. So in the Archean Eon, there are certain rocks that are common. First one we're going to talk about are the granite gneiss complexes. Then we're going to talk about greenstone belts. Then we're going to talk about banded iron formations, which are also called BIFs for short, in shorthand. And then stromatolitic limestones. So these are the four kinds of rocks, and you need to remember these are what we find in the Archean, from the Archean Eon, between 4 and 2.5 billion years ago. Let's first take a look at the first one, called granite gneiss complexes. Here's a typical granite gneiss complex. Here. This is another granite. Granite, you might remember, is an igneous rock. It's a plutonic rock. Cools underground. It's felsic. It's pink in color. And it's also got gneiss, G-N-E-I-S-S, which is striped. It's foliated. What these granite gneiss complexes represent is the first microcontinents that started to form during the Archean. So as these islands of continental crust collided, they grew together and to make bigger islands and to form little continents. And these are represented by these granite gneiss complexes. The granite gneiss complexes represent the initial formation of the continents. Granite and gneiss are found only on the continents. So this is ancient continental crust from the Archean. Next one we're going to talk about are greenstone belts. Greenstone belts are just what the name implies. They're green in color. And let me show you what they look like. They're made up of a rock called komatiite, K-O-M-A-T-I-I-T-E. And you can see that komatiite is kind of greenish in color, so it's ultramafic. These formed at very high temperatures, these greenish rocks. That's why we call them greenstone belts. Komatiite doesn't form anymore today. Why? Because the temperatures required to form komatiite are very high, above 12 to 1300 degrees Celsius. And the Earth has cooled down a lot since the Precambrian. But back during Archean times, the Earth was still very hot. And so we could form these ultramafic, ultra dark, green in color, lavas that erupted onto the surface of the Earth. So these komatitites represent ancient volcanic deposits, and they indicate that the Earth was much hotter than today. Greenstone belts. Here you can see some granite gneiss complexes, pillow basalts. We can also add that to our list. Pillow basalts are also found in the Archean, and pillow basalts. Whenever you hear the word basalt, think of the sea floor, because that's what the sea floor is made of. Pillow basalts. Here you can see the bottom of the sea floor. These mafic, dark in color, aphanetic pillow. They look like pillows that you sleep on. As the lava erupts onto the sea floor, it cools very quickly because of the water. It cools it quickly, and forming these pillow-like shapes. The bottom line is, since we found pillow basalts, that tells us that we have started to form sea floor or oceanic crust during the Archean. So the granite gneiss complexes indicate that the continents were beginning to form during the Archean. The pillow basalts indicate the sea floor was starting to form during the Archean. And the greenstone belts indicate that the Earth was very hot, so that we could erupt ultramafic lavas producing komatiite. Here you can see where we find greenstone belts in Canada, going all the way from Ontario to Quebec, all the way into the Northwest Territories, Manitoba. These are formed during the Archean, and you can actually go there when you go to Canada. If you're interested in geology, as I am, you can go see these greenstone belts, because this is the Canadian Shield, where you have these rocks exposed at the surface of the Earth there in Canada. So, in summary, so far we know that during the Archean, from 4 to 2.5 billion years ago, we started to form sea floor, as evidenced by the pillow basalts, and continental crust, as evidenced by the granite gneiss complexes, and the Earth was very hot, forming greenstone belts. Here's some greenstone belts found in Canada, going all the way into northern Michigan, and eventually these would collide together so that we started to form sea floor and continents. Let's see what else there is here, so I don't skip anything. Okay, so there's some other rock types that also are common during the Archean. Let's take a look at them. We got stromatolitic limestones. Okay, what in God's name are stromatolitic limestones? Well, you're about to find out. So limestone is as you probably remember, is a sedimentary rock made of the mineral calcite. When you added acid to it, it fizzed. Well, these structures that look like this, geologists know that these are formed by stromatolites. What are stromatolites? Well, let's take a look. Some stromatolites still exist on our planet. For example, this is a place in northwest Australia called Sharks Bay, and these are mounds, are filled with living things. They're tiny little creatures that make up layers in these, called cyanobacteria. Cyanobacteria are asexual creatures belonging to the domain Eubacteria, EU bacteria, and cyanobacteria are the, real important, ladies and gentlemen, the first evidence of life on planet Earth. At the moment, we have not found any more ancient fossils than cyanobacteria, which make up the layers in these stromatolites. So the stromatolite is the whole structure, but these tiny microscopic creatures, they'll die, and they'll form like a sticky mat, like a like a shag rug, and then sediment will accumulate and it'll form another layer, another layer. So inside one of these mounds might be 1,000 generations of these cyanobacteria that makes these mounds. We know that these form today using James Hutton's principle of uniformitarianism. When we see these same structures in ancient limestones, we know that these creatures existed in the past. Cyanobacteria are quite important. They are the first evidence of life on planet Earth. And they invented a new form of way of living, and it's called photosynthesis. So what is photosynthesis about? It's about taking CO2 plus water and forming glucose, which most people call sugar, and releasing oxygen gas. So stromatolites, this is called photosynthesis. Plants do it as well. They take in CO2 through their leaves, water through their root systems, and release a waste gas called oxygen. But it's a waste gas to plants, but it would eventually lead to an oxygen-rich atmosphere, which would allow for animals to evolve. But the bottom line is what plants are doing is they're making their own food. And that's why we call it. And so, but it wasn't plants who invented photosynthesis. The cyanobacteria invented it first, and later on the plants stole that technology, basically. Photosynthesis. So these photosynthesizing stromatolites started to add oxygen into the atmosphere during the Archean Eon. Fourth type of rock that's common in the Archean are BIFs, otherwise called banded iron formations. BIFs. Let's take a look at some of these. I bet you haven't seen these before unless you have been to Canada or northern Michigan or northern Minnesota. Here you can see they have bands in these sedimentary rocks, and there's gray bands, and in between the gray bands are red bands. These are called banded iron formations, and these are common during the Archean Eon. Banded iron formations, as the name implies, are made of iron. The red parts are made of oxidized iron, which forms a mineral called hematite. Chemical formula Fe2O3, which most people call rust, but geologists call hematite. The gray areas, though, the gray parts of the banded iron formations are formed of another mineral called iron mineral called magnetite, and that's Fe3O4. And magnetite is unoxidized iron. It's not rust. It's iron that has not rusted. So the red areas, there's rust, and the gray areas, the iron hasn't rusted. That's real important, ladies and gentlemen. Nowadays, if you take iron and you leave it outside, it's going to rust, right? There's too much oxygen in the atmosphere. Think about when you were a kid. If you took your dad's garden tools outside and left them out for a couple months, would they rust? Yes, because there's too much oxygen in the atmosphere. I did that once when I was 12 years old, and then my dad whooped me, and I didn't do it again. Anyway, the fact that we have unoxidized iron in these banded iron formations tells us that the atmosphere in the Archean was very oxygen poor. And I'm sure you have heard, if you've had any chemistry at all, that oxygen poor, we call it reducing. We had a reducing atmosphere, an oxygen poor atmosphere during the Archean. Why did we have an oxygen-poor atmosphere during the Archean? Well, where does almost all of the oxygen in the atmosphere come from? It comes from photosynthesis. And the cyanobacteria started to add some oxygen into the atmosphere during the Archean, but it wasn't enough to so that yes, some of the iron got rusted from the oxygen that was produced by photosynthesis from the cyanobacteria that were producing the stromatolitic limestones, but there wasn't enough oxygen yet. It would take more time before our atmosphere was so oxygen rich that we no longer form BIFs. BIFs are found in the Archean because the atmosphere during the Archean was oxygen poor. The last thing you want to remember of banded iron formations, or BIFs, is they are our main source of iron ore. Iron ore is very important. We make cars and trains and airplanes and so many things out of steel, and we have to mine this. Where do we get most of our iron ore from, do you think? What country? I'll give you a hint. Oh, Canada, my home and native land. Yes, from our northern neighbor, Canada. And we used to have a big iron ore mining operations in the United States, but we signed this really stupid trade agreement called NAFTA, and we gave the Canadians an advantage. But anyway, don't forget there's 5 main types of rocks found in the Archean: granite gneiss complexes, greenstone belts, BIFs, stromatolitic limestones, and pillow basalts. Let's take a look and see how our atmosphere formed. Our atmosphere is the gases above the surface of the earth, such as oxygen that allows us to breathe. And that's where all the clouds and weather occur. Well, where did the gases in our atmosphere come from? Almost all of it came from volcanic outgassing. As volcanoes erupted during the Archean, they released CO2, water, which would eventually collect to form oceans and rivers and lakes and clouds and cause it to rain. Nitrogen, 78% of our atmosphere is nitrogen. They all came from the outgassing, the gases that come out from volcanic eruptions. The only gas in our atmosphere that is not from volcanoes is oxygen, which came from those cyanobacteria, the first form of life on planet Earth as far as we know. Recently, a lot of scientists have been speculating that maybe some of the water on our planet also came from ice on meteorites and comets. NASA has sent space probes to various asteroids and meteorites, and we find that they're in large part made of frozen water. So maybe bombardment from these meteorites or comets added water too. That's also possible. So those are the 5 main types of rocks we find in the Archean. And in the next video, we're going to be talking about the first life on planet Earth as far as we know. And yes, we're going to be doing some basic biology because we have to do that in order to understand more about how life appeared and how it evolved.